Hi, everyone. Thank you very much for joining us today for our webinar with Testforce and Tektronix on automotive next-gen in-vehicle network standards. And we thank you. We encourage your participation. And if you have any feedback or other webinar topic suggestions for the future, then don't hesitate to let me know by the chat, or you can email us later at marketing@testforce.com. And before we get started, I'd just like to let everyone know that this webinar will be recorded and you'll be receiving an email afterwards with a copy of the recording. So you can go ahead and share it with anyone else you think would be interested or rewatch it if you'd like. If you want to see any of the other webinars we have on demand or that we'll be hosting in the future, you can visit testforce.com/academy. And if you have any questions during the webinar, please make sure you ask those in the Q&A section in the right side menu bar. You may need to click the 3 dots to get that box to pop up. And we'll be sure to get to all those questions at the end of the presentation. And now I'd like to introduce Darshan Mehta from Tektronix. His expertise are focused on electric vehicles, aerospace and defense, energy storage, and microgrid markets. So let's just mainly automotive. So let's just jump right in and get started talking about our topic today.
Thank you. Hello, everyone. Welcome to today's webinar on next generation in-vehicle network standards for the autonomous cars as well as infotainment systems. As all of us know that in-vehicle network standards are the backbone of the electronic system in the car. These in-vehicle network standards are very critical factor when it comes to the safety and the reliability requirement, which is the most important aspect for the autonomous car. So in this webinar, we are going to talk about what are the next generation in-vehicle network standards we have for these new applications like autonomous cars and infotainment systems, and what are the test challenges we will have when we are validating these standards, as well as we will talk about some of the test solution. So here is the agenda of today's webinar. We will start this webinar with the discussion on the automotive trends, and then we will move on that how these automotive trends are driving next generation of in-vehicle network standards like the Automotive Ethernet as well as some of the LVDS standard. And as you can see in the speed of the Automotive Ethernet, now we have all the way from 10 Mbps to 10 Gbps Automotive Ethernet standard. So as we move transition from the low speed in-vehicle network standards like CAN, CAN-FT to this high speed network standard like Automotive Ethernet, we will talk about that what kind of test challenges we may have, what kind of test requirements we have to perform the compliance as well as system level test for these standards. And we will have the live demonstration also for all these different standards with respect to the compliance test as well as the system level signal integrity measurements. We will also cover some of the LVDS standards which are used for the display and the camera interface, and what are the test requirements for that as well. So let's start with the first topic, which is the trends. So there are three main applications in the automotive world, which are in the which we all of us are probably dealing with. The first one is the electrified car. So in the electrified car, one of the biggest challenge team is evaluating is how do we increase the efficiency of the battery with the single charge, how long we can drive. The second one is the cost. How do we overall reduce the cost of the system so that the electrified car is affordable in the market and can compete with the current solution as well. And in this area, the teams are working on evaluating various different components which will improve the power efficiency, reduce the battery size, as well as overall weight of the car. The second application is the autonomous car. This application is mainly motivated from the safety aspect. As all of us know that 95% of the car accidents are because of the human error. So we are evaluating that with the autonomous car or a smart machine inside the car, which will either assist the driver or replace the human driver and make all those decisions related to your safety. And that will make the driving much safer. And to achieve this, functionality or have a smart machine in the car, we need a combination of sensors. So sensors are nothing but they will provide a 360-degree view around the car, that what are the objects around it, which will help making those decisions. Along with those sensors, we will have a complex embedded controller, which is going to take all the sensors data and then make the smart decision that whether to apply the brake, change the lane. So all these smart decisions will be done by the smart machine inside the car. Now, to achieve this functionality, as you can imagine that now we are replacing a human driver with a smart machine. And for to achieve that, it requires a very high speed controller, because in a matter of time we have to make those decisions. It is almost like replacing a brain with a machine. So now we have to deal with very high speed controller in the car along with the sensor network. Could be multiple sensors to achieve this requirement. And that requires a huge change with respect to the architecture, the speed of the in-vehicle network standard as well to meet the latency requirement. The third one is the connected car. And in the connected car, there are vehicle to vehicle, vehicle to infrastructure, or vehicle to anything. And in short, this is called as a V2X as well. The main motivation for the connected car is for the road safety, traffic efficiency, and the energy saving. And with this connected car, there will be multiple wireless standards like the 5G, the wireless LAN, also ultra wideband. Those all different wireless standards along with existing Bluetooth, will exist. So as a validation engineer, we have to validate a complex embedded hardware along with the presence of all these wireless standards. The most common challenge in the automotive world is that the life cycle of this entire design flow is anywhere between 3 years to 4 years, depending on the complexity of the design you have. And in this entire validation workflow, we have to validate each component as well as system level. So, and all this needs to be attained in the limited resources and the tighter timeline. All of us are having a resource problem as well as the time we have to meet the tighter timeline. So, and apart from all of this, in the automotive electronics, we have to meet the reliability criteria and the safety criteria. So the validation for the embedded world is, if it is 2 months, for the automotive, the test metric grows 4 times, and the validation times grows anywhere between 4 to 6 months to meet those safety and reliability criteria. In today's webinar, we are going to focus on the autonomous car. We will talk about what this autonomous car structure will look like, and what are the different standards which are evolving because of the autonomous cars. So let's start with the basics. I'm sure you will be familiar with this slide. What's the autonomous car? It is also called as Advanced Driver Assistance System, in short ADAS. There are 5 levels of the automations, level 1 to level 5, and depending on the level, the responsibility of the machine will be, or the responsibility of the decision making will be transferred to the machine. As you can see that in the level 5, the entire decision making responsibility is with the machine. So there is no driver at all. Human driver is replaced completely by a machine. So all the critical decisions will be taken by this smart machine. Now, as we move from level 1 to level 5, the machine becomes more and more smarter, and we need higher speed controller and more number of sensors to meet those complexity. Like for the level 1 and level 2, we can have a simpler architecture, but as you move to the level 3 to level 5, the architecture becomes more and more complex. And we'll talk about what are the complexity we may have as we go to level 3 to level 5. So this is the architecture block diagram of the autonomous car. There are 3 main blocks in this architecture. It's called as a sensor block, which is automotive radar, camera, and LiDAR sensors. Then there is a controller and then actuator. So the way it works is that there are three different kind of sensors used: radar, camera, and LiDAR. And depending on which level of automation we are trying to achieve, the number of sensors will increase. Like level 5 may have 10 to 16 cameras, similar number of radar and LiDAR camera sensors. So all these sensors are looking at a 360-degree view and giving information to the controller that what are the objects nearby. Those kind of information is provided to the controller. You can imagine that any of the camera or radar sensor, they are operating at very high speed. And to transfer the data from the sensor to controller, we obviously need high speed in-vehicle networks standards to send this raw data to the controller. The second one is a controller which is making those data crunching and doing the decision making. So again, you can imagine that 16 camera sensors are sending data simultaneously to this controller, and then it has to make the decision in very short time, like a 4 microseconds or even lesser than that. So we need a faster complex embedded hardware to meet these requirements. And then you have the actuator systems to communicate the decision whether to apply brake or increase the acceleration. This controller sends the information to actuators system, which could be a low speed network standard. So in general, in the autonomous car, to achieve level 1 to level 5 autonomous cars, the architecture and the electronics which is required for this is going to be very complex. Currently, we have like hardly 200, 300, or 700 megahertz kind of controllers in the ECUs, and those will be replaced with the much higher speed controllers in terms of terahertz also. If you move to the architecture part, even there is a architecture level difference required for to meet the latency requirement. So I've described here three different architecture. The traditional one, which is currently used. In the current architecture, all sensors and the respective ECU, they sit very next to each other, and the decisions are done by the sensor, and these are called as a smart sensor. So in this case, the raw data is not sent to the gateway or the controller, while individual sensors have their own controller to make the decision. So that architecture has its own advantage and disadvantage. The disadvantage that all sensors are making their own independent decisions. They don't know the data from other sensors. So it is not a collective decision. It is individual sensors decision. But for the level 3 to level 5, that architecture may not work. So other two architecture which are under considerations are the central computing and the zone architecture. In this, the most popular one is the zone architecture, where we will have probably 3 or 4 different zones, and each zone will be doing data processing from their individual sensors, and then they would be talking to each other through high-speed network standard to communicate each other that what data they have received from sensor and what decision they should make. So there could be like 3 to 4 different zone. This is called as a domain controller also. So this is the one architecture which is very popular. There are a few OEMs who have already announced that they would be using a zonal architecture or a domain controller architecture using this one. So in the advantage of the zone architecture is that now instead of having 60 to 100 ECUs, we can replace all of them with 3 or 4 different controllers. So that reduces the complexity. But obviously, we have to look into the redundancy part also. That how do we achieve the redundancy using this architecture? The bottom line of all this different application is that like if you look at the zone architecture, now those two ECUs needs to communicate to each other with a high speed. So with all this application, we need much faster network speed compared to what we have currently, like a CAN FT, which operates like between 2 to 4 Mbps. That speed may not be sufficient to meet the requirement of the autonomous car. We need much faster speed than that. The other application we are seeing is infotainment. This is one area where we need a much faster in-vehicle network standards compared to what is available today. Previously, we had a smaller display in the car, but in the latest car, if you see, we have the bigger display and an infotainment system. So currently, we are at second generation of the displays, but in the future, we are likely to see even a 4K kind of display, which will need a 24 Gbps kind of a net streaming speed to send the video and display on the display panel. So which means again our traditional CAN FT standards may not be sufficient. We need a faster in-vehicle network standard for this streaming application. So now let's look at what are the new in-vehicle network standards we have to meet the requirements of the autonomous car as well as the infotainment system. So first let's start with the basic. What is in-vehicle network standard? So any electronics in the car, they communicate with each other through a vehicle network standard. It's a very similar to like two laptops talk to each other through a LAN or a wireless LAN. Similarly, in the car, the electronics component, it could be sensor to ECU or a ECU to ECU. They communicate with each other through a vehicle network. There are many vehicle network standards which are already used in the car, like CAN FT, FlexRay, LIN, but all of them are low speed. With this new requirements from the autonomous car as well as connected vehicle, we have two more new requirements. One is from the zone architecture. We need a symmetric high-speed communication. Symmetric is nothing but where uplink speed and the downlink speed is the same. It's very similar to PCI Express, where the transmitter and receiver are communicating with each other with the same speed. So for the ECU to ECU communication, we need a high-speed symmetrical communication. For the camera and display kind of application, we need asymmetric high-speed communication, because in case of camera, we don't need uplink and downlink to be same speed, because it's more of a streaming application. So we need maybe high speed on the uplink or and low speed on the downlink. So we don't need full speed on both uplink and downlink. So that's another requirement. The most important or the fundamental requirement of in-vehicle network standard is the reliability. As you know that in-vehicle network standards are exposed to the harsh environment of high temperature and high vibration, high noise. So, and it has to reliably send the data from one ECU to other ECU. Any bit which is corrupted, it can cause accident as well, right? So the bit error rate requirement for in-vehicle network standard is anywhere between 10 raised to minus 12. That's the error rate we need to achieve. And we need to make sure that it reliably sends the data even in the noisy environment. We will have a lot of noise source in the car, from various parts, like even in the batteries which are used that can emit noise. There are wireless standards also which are communicating with the car. So we need to make sure that even in the noise environment, the in-vehicle network standards meet those reliability requirement. And obviously it has to meet the EMI, EMC requirement, low weight, low cost, and low power. It has to make sure that the in-vehicle network standard consumes less power, because ultimately car is operating on a battery. So that's something is very, very important when we select any in-vehicle network standard for the newer application. So these are the most important criteria we look at before selecting any in-vehicle network standard for the application. Let's look at some of the new in-vehicle network standard which are evolving. I'll start with the symmetric in-vehicle network standard, where it offers a full speed, full uplink and downlink speed. So in that, Automotive Ethernet is one of the fastest growing standard. It has currently IEEE is defining this particular specification along with Open Alliance. So we have already 100 based T1, which is 100 Mbps, 1 Gbps Automotive Ethernet standard, and multi-gigabit Ethernet, which is 10 Gbps. This is the latest edition from the IEEE. It is approved specification. which was released by IEEE this year. So these are the three standards which are already approved from IEEE. And then IEEE is working on next generation 25 and 50 gig automotive Ethernet also for ECU to ECU communication. In the asymmetric IVN standard, there are various LVDS standards available like FPD Link, GMSL, and all of them are like proprietary standards from OEMs. There are few standards bodies also working on defining asymmetric IVN standards like MIPI Alliance is working on MIPI A5. There's a standard called HT-BST, and latest one is ASA. So these all standards are likely to be used for the display and the cameras as well. Even multi-gigabit Ethernet have a version where it can operate in a half duplex mode, which can be used also for the display and the camera. There are also some transitioning on the low speed in-vehicle network standard also, like a 10 base T1S, which is also automotive Ethernet. It operates up to 10 Mbps. There's another standard like CAN XL. So all these new standards which are defined by various standards like MIPI, HT-BST, and Open Alliance. So previously we had most of the proprietary standard in the in-vehicle network standard. So automotive world is moving to a standardization, and Tektronix is part of most of these consortiums and driving the test specification. Let's deep dive into the automotive Ethernet, which is one of the fastest growing standard used for various application. So as I mentioned, there are speed, automotive Ethernet have 10 Mbps to 10 Gbps already approved specification. So in this section, we'll talk about what are the different speed gates it offers and what are the test requirements. So, so these are all the IEEE specification versions for various test speed, starting from 10 Mbps to 10 Gbps. One of the reasons it is the most popular one is that it offers the full duplex communication on the single cable. I gave example of PCI Express, which is also is a symmetric communication. But in PCI Express, you have a transmitter lane, you have a receiver lane. While in this case, on a single lane, it can operate on a full duplex. So that reduces the cable cost by almost 80% and weight by 30%. So that's the biggest advantage of automotive Ethernet. It offers that single pair of cable. It offers full duplex communication. And it's a great advantage, but from the test point of view, there are some test challenges with the full duplex communication, and we'll talk about that in the next section. The second advantage of this is that this automotive Ethernet is a derivative of the traditional Ethernet. So except the physical layer change, everything else like layer 2 to layer 7 is more or less similar to the traditional Ethernet. So we can reuse, it's a proven technology used in the Ethernet world for so many years. So we can reuse lot of applications when we move to the automotive Ethernet. So only, we have made few changes in the physical layer to meet the requirement of the automotive standard. Like we use PAM3 modulation in the automotive Ethernet. So that's the biggest advantage of this one. And the third advantage that automotive Ethernet offers the variety of speed grades. As I mentioned, we have starting from 10 Mbps all the way up to 10 Gbps, and in future we'll have even 50 Gbps in the automotive Ethernet. So with this, same architecture, you can have speed from 10 Mbps all the way up to the high speed. So that's the biggest advantage also of the automotive Ethernet. This is a summary of all the different speed gates. So we have the 10 Mbps, which operates in the half duplex only, and it can be configured as a point-to-point or a multi-drop also. So you can have like 8 devices connected to a single master. So it can go all the way up to 25 meters as well. 100 base T1 and 1000 base T1, they operate with a PAM3 modulation. The advantage we get with a PAM3 or a PAM4 modulation that one is, it reduces the bandwidth requirement of the cable because now it's a modulated signal. And because it's a PAM3 signal, it has a slow rise time. So it reduces the power requirement as well as helps meeting the EMI EMC requirement. And that's the reason, we are using PAM3 or a PAM4 kind of modulation for automotive Ethernet. This operates in a full duplex, so it's a bidirectional and sends and receive data simultaneously at the full speed. 100 base T1 and 1000 base T1 use the unshielded twisted pair of cable up to 15 meters. Multi-gigabit Ethernet, which is the latest edition, operates up to 10 Gbps. It has three speed gates, 2.5, 5, and 10 Gbps, and it has a PAM4 modulation. The voltage range is 1.3 volt. Is the same as 1000 base T1. But here one of the catch is that now we are sending 4 bits or 4 level of signal within 1.3 volt. So you can imagine that we are sending more number of bits now in the same voltage level. So this is going to be more challenging with respect to doing the noise testing. That, as you know, that we have to make sure that when there is a noise on top of the signal, how it is impacting the receiver. Are we able to still detect one as a one and a zero as a zero? So here we are sending like 4 level of signal within 1.3 volt. So noise testing is also going to be very critical at the system level. Um, so now let's look at the test requirement for automotive Ethernet. For CAN FT, we never had any compliance test. We had more like a test requirements from the OEM, and we have to perform eye diagram test as well as noise test and some of the rise time, fall time, timing measurements. When we come to automotive Ethernet, now we have the compliance test as well. And this compliance test is defined in the IEEE as well as the Open Alliance test specification. So we learn about what are the compliance test requirement. The second requirement is a system level performance test. So when you integrate two ECUs, and you add a noise on top of it, are you able to? Is your receiver is immune to that noise? And the noise could be either a voltage noise or it could be electromagnetic noise. It could be the performance test, like if you have a 10-meter cable versus a 15-meter cable, is your receiver still behaving okay with this? What should be the cable optimum cable routing? So those kind of system performance tests we need to perform. And the last one is a protocol test, which are mostly to do with the timing measurements, and we'll talk about all these test requirements in the next few sections. So let's start with the compliance test. So in the compliance test, as I mentioned, there are two different consortiums involved, IEEE as well as Open Alliance. So it starts with the definition of like IEEE develops the specification, which has the complete like protocol as well as the physical layer definition. And they define the test specification as well for the physical layer as well as the protocol level as well. Now, Open Alliance looks at or takes the IEEE as the base spec and develops two kind of specification. One, they call it as a physical media attached test or a PMA test, and second one is for the ECU level. It is called as a TC8 specification also. So one is at the component level and the other one is at the system level or an ECU level. So for the 100 base T1 and 1000 base T1, we already have the test specification for the PMA and the TC8 specification also. While for the 10 base T1S and the multi-gigabit Ethernet, the Open Alliance test specification is still in the discussion, while the IEEE specs are already available. So as a user, now the question is that what spec we have to follow. So typically the PMA transmitter tests are pretty much similar to the IEEE specification only, but Open Alliance defines the procedure also, like what should be the record length of the oscilloscope. Those level of detail test procedure is defined by Open Alliance, but the test limits are similar to IEEE specification as well. When you move to the TC8 test specification, there could be additional ECU level test parameters which we have to perform. So depending on whether you are validating the component or an ECU, we have to follow a specific test standard. So let's talk about the PMA transmitter test. So for the 10 base T1S, 100 base T1 and 1000 base T1, these are all some of the tests which are defined in the Open Alliance. And Open Alliance also defines the test procedure that to perform this measurement, what should be the setting on the oscilloscope, what should be the setting on the arbitrary function generator, and what are the test limits against which you should perform the test. It also defines that what test mode we need to configure in the device under test to perform this procedure. So let's go to few tests which are the most critical one. Let's start with the distortion test. So in the distortion test, the way we have to perform this test is that we add a disturber signal on the DUT, and then look at that how immune your signal is with respect to this disturber source, so disturber signal. And the way this test procedure is defined in the Open Alliance as well as IEEE spec is that we have to synchronize the whole setup, which means that we have to extract the clock signal out of the DUT, and then that signal needs to be fed into the oscilloscope as well as the disturber source, and that will make sure that we have synchronized the whole setup. Now, one of the biggest challenge we may have is that many a times at the ECU level, we may not have access to that DUT clock because it's an enclosed box. So we have a distortion test which supports both hardware-based method where we can synchronize the whole setup, or using the software method also, in which you don't have to extract the clock and synchronize the whole setup. The software itself can find out the edges and perform the distortion test, or find out the disturber signal to perform this measurement. And in this, the advantage you get is that you don't have to use any clock from the DUT to perform this measurement. We will see this in the demonstration also, that how our method helps you performing this measurement without accessing the clock as well. The next three measurements we are going to talk about are more of a frequency domain measurement, where we need a spectrum analyzer or a vector network analyzer kind of instrument. But Tektronix offers this measurement using the oscilloscope itself. So the first measurement in that category is a power spectral density, where we have to plot RF spectrum to calculate the power spectral density. And we use the oscilloscope FFT method to perform this measurement. Our oscilloscope offers the lowest noise floor with a 10-bit ADC, so that you can perform this measurement and get pretty much correlated results with the spectrum analyzer. We have done correlation with the spectrum analyzer, and it matches with the performance of the spectrum analyzer. So we are able to perform the power spectral density measurement using the oscilloscope itself. The second measurement we have is the return loss measurement. So whenever you think of return loss, obviously the choice is a vector network analyzer. But Tektronix has a patented technique by which we perform even the return loss measurement using oscilloscope and a function generator. And we use this technique for the traditional Ethernet also for more than 10 years. So, and we have done correlation with the network analyzer as well. So it correlates the result. The reason this method is pretty much applicable for automotive Ethernet, because if you see the spec limit, those are not asking for like minus 80 dB loss or those kind of measurement. Those are in the range of minus 20 to minus 30. So that's the reason even the oscilloscope based method is able to measure this return loss for the automotive Ethernet. And our performance is very similar to vector network analyzer. Here the advantage for you is that with a single instrument you can use for the time domain measurement as well as some of the frequency domain measurement as well. Another measurement we have, which is common mode emission test. Again, as per the Open Alliance procedure, you can use either oscilloscope or a spectrum analyzer for this measurement. So again, we use oscilloscope method to perform this common mode emission test. This specification have a very tight margin, like a 25 microvolts up to 200 megahertz, and it is very sensitive to the noise from nearby instrument or a monitor or even the mobile. But we are able to perform this measurement using the oscilloscope and accurately measure the common mode emission as well. So these are the three measurement where it is a frequency domain measurement, but we are still using an oscilloscope to perform this measurement. Let's look at the solution. So what solution we have? So there are three different aspects of the solution. The first one start with the fixture, second one is a probe, and third one is the oscilloscope along with the automation software. So we have a Tech Express based automation software by which we can automate all the measurements for the automotive Ethernet and perform the compliance for 10 base T1S, 100 base T1, as well as 1000 base T1. This particular solution is supported on the 5 and 6 series MSO, which is the latest oscilloscope, as well as the performance oscilloscope like the DX and SX series platform also. So let's talk more about the Tech Express based solution. So it's a wizard based solution. Here the biggest advantage that you don't have to read the documents from IEEE or from the Open Alliance. This configures the entire test based on the automation platform. So in a single Tech Express software, we have 10 base T1S, 100 base T1, as well as 1000 base T1. Once you select the specific test suite, you can configure the test selection. So we have all the tests as per the Open Alliance as well as IEEE specification. This application can run either in the compliance mode or the user-defined mode. So in the compliance mode, it configures the parameters of the oscilloscope or a function generator completely as per the Open Alliance procedure definition. In the user-defined mode, as an advanced user, you can change most of the parameters to perform the test beyond compliance. One of the biggest advantage you get with this solution that every time you run this measurement, the waveform, the oscilloscope setting, as well as the report, everything is saved into the hard drive as a session file. So in case you find a failure, you can recall those session file, which will include the waveform, and you can perform the debug. We offer a DPOJet debug tools as well to perform root cause analysis, that why certain test failed in that. You can share this session file with your counterpart team to run this in an offline mode and perform the analysis that why something failed. Once the measurement is completed, it gives you a nice report along with the pass-fail criteria, whether the test is within the limit. It also gives you a screenshot that how this measurement was performed and what region of the waveform this measurement was performed. So all these parameters will be available, which can be shared with your counterpart team. So let's move to the next one, which is the eye diagram test. We mentioned about the system level test requirements that we need to perform a noise test, that when you integrate two ECUs, how these two ECUs are communicating with each other, and if you add a noise, is there a performance deterioration? So to perform this measurement, um, first thing is that why do we need eye diagram test? Is it defined in the Open Alliance or IEEE? Yes, the noise test is defined in the Open Alliance, that you need to add a noise and perform the signal quality test at the receiver. And as you have seen that many of the high-speed standard, like we take PCI Express or USB, all the standard, one of the critical measurement is eye diagram, because eye diagram gives you overall health of the link, that how this link is performing in various condition, like a noise or a change in temperature. change in voltage, how the eye diagram gives you a good view of the overall link. Even for CAN-FT kind of low speed standard, we perform eye diagram test just to make sure that because of the multiple nodes, is it the loading affecting the rise time or a fall time of the signal. So even for automotive Ethernet, eye diagram will give you a clear view about the link health, that how good the link is and what could be the bit error rate if you add a certain amount of noise. One of the biggest challenge with the automotive Ethernet is that if you want to perform an eye diagram test or even a protocol decode test, if you connect a probe on a transmitter or a receiver side, you will see a close eye diagram. If you have noticed this anytime you just connect the voltage probe and probe on see on the oscilloscope, you will see a completely closed eye diagram. The reason for this is that, as I mentioned, it's a full duplex signal, which means transmitter and receiver are sending data simultaneously on the same link. So when you probe on any of the node, the signals will be overlaid. So we will not be able to get any meaningful eye diagram or a protocol decode if you just connect a voltage probe. So our first step for doing signal integrity analysis or a protocol decode is doing a signal separation. So what do we have available today? So the solution available today is using a directional coupler. So directional coupler has a property that even in a full duplex environment, it can separate the transmitter and receiver signal. But directional coupler is an external hardware. And to use this particular hardware, we have to cut the cable and then insert a new hardware in between, right? And the directional coupler, most of the directional coupler are SMA based. So we need to convert the automotive Ethernet cable into SMA, then add a directional coupler to perform this particular measurements. The other challenge with the directional coupler is that it has a huge insertion loss, and also it is going to impact the mode conversion also. So it's going to load the ECUs as well. So if you use a directional coupler, you may not be able to get a good signal performance. And if there is a failure, then it could be because of directional coupler. We don't know. Now we are adding a new variable into our ECU system. So that's not the best approach to do an eye diagram test. So Tektronix came up with a new solution where we don't use a directional coupler or an external hardware which cuts the cable to perform the signal separation. We introduced a new method where we do signal separation in the software. So along with the voltage probe, we sense the current as well. And using the direction of the current and the signature of the voltage and the current waveform, we are able to separate the traffic of transmitter and receiver using a software technique. And we introduced this solution last year. We won an award of the best new product introduction in the test and measurement category. So we have already quite a few customers using this solution for doing the signal integrity analysis. Um, and the biggest advantage we get with this approach is that you don't have to cut the cable, very easy to use, and there is absolutely no loss of the signal because of any insertion loss or any loading on the ECU. We can easily connect the current probe and separate the transmitter and the receiver signal. This solution is available for both 100 base T1 and 1000 base T1. And we recently added the equalizer support also. So let's say you have the far end signal here, which will have the cable effect. You can apply an equalizer and then remove the effect of the cable as well. So you can see in this screenshot that the top one is the full duplex signal. You can clearly see it is not a PAM3 signal, it is overlaid signal. Um, the red color one is the current waveform, and using the voltage and the current waveform full duplex signal, we applied the signal separation algorithm, and you can see bottom two signal are now PAM3 signal. You can clearly see three levels. So the top one is the transmitter or a near end, and the bottom one is the receiver signal, which has, you can see a little bit of ringing effect because it has travel through a cable. So this ringing effect is because of the cable. If you apply a receiver equalizer on this, then you can remove this ringing effect also. And you can see the voltage levels also. It is approximately 2 volts peak to peak here, and that's the 100 base T1 amplitude. So you can clearly see a separated signal without cutting the cable using this technique. Here's a comparison of the signal separation based software based signal separation versus a directional coupler. So first thing you can see is an eye diagram. Here we have used a 15 centimeter cable, and we have an eye diagram. And one is with the directional coupler, other one is with the without directional coupler. And you can clearly see that even with a very short cable, we see eye diagram deterioration. If you use longer cable, then the further the eye will be deteriorated in case of directional coupler. You can compare the amplitude. We get 2 volts peak to peak with the signal separation without doing any de-embedding, but while in this case we get only 200 millivolts. So we can do like de-embedding here, but now we are talking about 10 times, right? So when you do de-embedding up to 10 times, even the noise is going to be multiplied 10 times. So our signal to noise ratio is going to be impacted by doing this. And the most important, it is very easy to set up. You don't have to cut any cable, or you don't have to add new hardware in between to perform this signal separation. And this waveform can be used for doing a signal integrity analysis as well as protocol decode. Let's look at a short demo of this feature. Um, and I'm going to do voiceover. I've just recorded this video and showing a demo, live demo of this one. So we have the two Marvell DUTs here, which are configured as a full duplex signal. One of them is acting as a master, another one is configured as a slave. And then we have connected a twisted pair of cable between them, a short cable for this. Obviously, we can use the same demonstration for the longer cable as well, and it works. And we have connected the TCP0030 current probe and TDP 1500 voltage probe as a differential signal, and one is as a single-ended. And the direction of the current is from a positive side of from master to the slave. That's how we have connected, and we have connected the voltage probe also differentially. So now let's look at the application. So we have this TechExpress application again for the signal separation. It can be done as a 100 base T1 or 1000 base T1. In this demonstration, we will add an equalizer also to show you that how it affects removes the ringing effect. So we have a 3-tap CTLE filter and created that filter. And now we are going to press the validate to perform the signal separation. So now it will acquire live waveform. One is on the channel 1, we have the voltage waveform, and on the channel 2, we have the current waveform. So it will acquire both the waveform and now perform a signal separation on this. So again, we are using a patented technique to separate a transmitter and the receiver signal. It is applying the filter as well, and then doing a clock recovery. And based on these waveforms, it will plot an eye diagram for both transmitter as well as the receiver. So here the left hand side is the transmitter, and the right hand side is the receiver eye diagram. So you can see some ringing effect on the other eye diagram, just to show you that before equalizer and after equalizer, what was the difference. So let me pull in the waveform without filter so that we have the comparison of both. So this is the eye diagram before applying the CTLE filter, and we'll do it for the near end as well. So this shows the comparison that how easily we can capture the signal using this setup and then perform the signal separation as well as eye diagram. This eye diagram can be used like if you add a noise, then how the eye diagram looks like. It calculates the bit error rate as well, that with the given eye diagram, what could be the bit error rate also at the receiver end. So you can extrapolate this information to look at that, what could be the bit error rate. This eye diagram can run in a continuous mode as well. So, you can run continuously now, and it will keep acquiring the waveform and plot an eye diagram. And for every eye diagram, it will give you that what's the bit error rate for this. So you can see like it runs in the live mode also and keep capturing the eye diagram. So that was a quick demo of the signal separation technique. Now let's move to the other use case, which is the timing measurement. So as we are moving to the automotive Ethernet world, we will have the gateways, and the gateway are basically are communicating with the existing low speed CAN FT network and converting into automotive Ethernet. So one of the test requirement for us that what's the latency of when you send data from CAN, how much time it takes to reach to the final node. So that's a latency measurement. The other one could be that for the automotive Ethernet, we have the MII interface, or a media independent interface, which converts the MCU data into automotive Ethernet. So what's the latency of MMI to automotive Ethernet? So for such measurement, also we can use this signal separation technique. So in this scenario, in the demonstration, what we have done is we've used Intrepid CS box as a gateway, and then we are simulating a scenario where we are sending CAN traffic on one node, and then it is converted into automotive Ethernet, and we are calculating the latency, overall latency of that. So again, we are using a signal separation technique to perform this demonstration. So let's look at a quick demo of that as well. So here we have the Red Galaxy box, and this is a vehicle spy UI. So in that we have programmed multiple CAN sensors like a speed sensors and temperature sensors, and then we are using a functionality of vehicle spy which converts CAN to Ethernet or a CAN to TCP. So that's the functionality we are using to show this demonstration. So when you say transmit, it is going to send this CAN traffic into the automotive Ethernet. So once you click on that, we are sending a data called 70 as from the speed sensor onto the automotive Ethernet. So we have sent the data, and we have programmed, as you can see, we have sent 70 here as a data from CAN to automotive Ethernet. If you see the hardware connection, we are using this Red Galaxy box, and we have on one side, we have connected on the CAN port to sense the CAN traffic. And then with respect to the CAN, we are probing on the automotive Ethernet as well. As you can see here, again, we are using combination of voltage probe and a current probe to use sense the automotive Ethernet traffic as well. So we're using this non-intrusive method of signal separation. Now let's look at the oscilloscope. So we are triggering on CAN bus, and then looking at performing a timing that from CAN to automotive Ethernet, how much time it takes. So it has calculated 179.2 microseconds. So as you can see, here is a CAN traffic, and the top one is the automotive Ethernet. So with this technique, we can do precise timing measurements without cutting any cables and without compromising on the performance of the ECU, and perform the protocol decode for both automotive Ethernet and the other standards as well. Okay, so now let's move to the next section, which is the IVN standards for the camera and display. So there are two kind of standards which exist today. One is called as a a device vendor or a proprietary standard, which is FPD-Link, GMSL, GVIF. And as I mentioned, there are multiple standards which are working on this one called MIPI A5, ASA, HT-BASE-T, multi-gigabit Ethernet, as well as Japan-based Jasper standard. All these standards are also working on standardizing these interfaces. Um, this standardization is still in progress, so we don't have like a real silicon available today for any of these standards. There are a few which are available, but most of them are not yet available in the market. So in this presentation, we are going to talk about the proprietary standards like FPD-Link or GMSL. So if you have those interfaces, one of the biggest challenges is that, now there is no consortium or no compliance standard, right? So how do you measure it? Is there a test procedure available? And is there a documentation available to perform measurement for some of these proprietary standard? So, so Tektronix have come up with very unique way of solving this problem, that we have two ways to perform this measurement. One is we have a DPO jet, which is the eye diagram and jitter test tool. So based on the this DPO jet tool, we have already developed some of the basic measurement for these standards like FPD-Link, GMSL, and GVIF. So and we have the standard set of files available to perform those measurements. We work very closely with most of these silicon providers, and then develop this setup a file-based solution. The second one is we have the Tech Express based solution called LVDS Express, and this is a completely user-defined test solution. There are already quite a few tests available for the LVDS standard, and the most advantage of this one is that all these test limits are user configurable. So if you have the test limits available for any of the standards, you can program the test limit and perform the transmitter analysis for the some of these proprietary standard as well. So, this is the last slide about the summary that we offer a complete transmitter test solution from 10 Mbps, like a 10 base T1S, all the way up to 1 Gbps automotive Ethernet, and not just the compliance solution, but also some of the LVDS standard transmitter validation solution for the FPD-Link and other proprietary LVDS standards. And beyond compliance, obviously just, component test is not the only test you would be performing. We have to worry about the system performance, that if you add a noise, how the eye diagram would look like. So we offer a solution beyond compliance for the system level test solution also. And we offer various debug tools like a DPO jet, PAM3 analysis or a PAM4 analysis, signal separation, protocol decode, to perform not just pass fail test, but if something failed, then what could be the possible root cause of that. So if, let's say, the signal quality test is failed and you want to see an eye diagram, we have the signal separation solution which will give you an eye diagram, and you can plot the various different measurements as well. So we are beyond compliance offering the solution. With respect to the consortium participation, we are active members in most of the consortiums we mentioned. We drive the test specification. Tektronix is leading the Open Alliance multi-gigabit Ethernet PMA test specification development. So we are active contributors in many of the consortiums to drive the test requirements. And last but not the least, we just announced the new oscilloscope in the MSO6 series just yesterday. So this offers a 10 gigahertz analog bandwidth along with up to 8 analog channels. So it offers the lowest noise floor along with the high 50 gigasample of sampling rate. And with respect to the automotive solution, this one box can be used for the multiple applications. So we already spoke about some of the applications on the in-vehicle network standard, but apart from that, the same box can be used for the automotive radar analysis, as well as inverter motor drive analysis and the power analysis solution. So we want to make sure that you can use the same capital investment for multiple application. And these are some of the reference. You can go to this link and find out more about this application. And also, if you are interested to know more about automotive radar solution or a power solution, feel free to contact me. We're almost on time, but this is my email address and my LinkedIn profile. So in case you want to connect with me on any topics you are interested in, I'll be happy to share more information on those topics. Um, so I'm sorry that we took longer time, but if there are any questions, I'll be happy to address them.
That's great. Thanks so much, Darshan. And on the topic of the new MSO at 6 Series B, I wanted to let everyone know as well that we're going to be doing a insiders launch party next Tuesday, Electronics. And so when I send out a copy of the recording in the next day or so, I'll include the invitation link for that as well. So Darshan mentioned how it relates to automotive, and I think in the launch party, you'll have a chance to win some fun stuff too. So I'll include a link to that in our follow-up email you'll get in the next day or so. Now, Darshan, there's one question that came in. How would this be used for automotive radar in the millimeter wavelength range?
Okay, good question. That this bandwidth was 10 gigahertz. So the way we use is we have a down converter which down converts the 76 gigahertz all the way up to 4 gigahertz, 4 to 8 gigahertz range, and then we do all the analysis using this very low noise and 10-bit dynamic range it offers. So we do all the automotive radar analysis using this particular oscilloscope along with the down converter. And I'll be happy to share more information. Please contact me on the email and I can send you some more details on that.
Perfect. Thank you. And I think just another question as well. In the compliance application, do you offer programmatic interfaces to automate using Python?
Oh, great question again. So the Tech Express application, which we covered today, has all the commands can be controlled through programmatic interface. We give you a manual which have all the command to program or control those functions using the Python or any other programming language as well. So you can actually include the Tech Express into your automation platform as well using Python or any other language and automate further on top of it. Yeah, it's possible to do that. Good question.
That's great. Thank you. And to anyone else, if you think of any questions after the webinar is over, don't hesitate to email Darshan, or you can email me as well, just to make it easy. It's marketing@testforce.com, and I'll make sure that I get you any additional resources or put you in touch with the people who would be able to help you with that. So thanks again, everybody, for your time. Much appreciated. And we look forward to hearing from you all. I hope you have a nice day and stay safe. Thanks, everybody.
Thank you, everyone.